Graphing reciprocal functions. Reciprocal functions by true definition are the reciprocal of a linear function. Now, I'm not going to write out their technical definition because that generally doesn't really help people. Things you need to know about reciprocal functions. First off, their parent function. Do y'all remember what it means for a function to have a parent function? It's the most basic function in the family. The most basic of the reciprocal functions is f of x is equal to 1 over x. Because it's the reciprocal of the linear parent function, which is f of x is equal to x. Now, when it comes to these reciprocal functions, their graph is known as a hyperbola. And a hyperbola will look something like this. Here's my x and y axes. A hyperbola is a type of graph that's broken up into two parts. It looks almost like two parabolas, kind of opposite or diagonal from one another. That is our f of x equals 1 over x function, assuming, of course, that it hits the coordinate point 1, 1, and negative 1, negative 1. Now, when it comes to these hyperbolas, they have a line that the graph approaches, but never actually reaches. That should be a term that sounds at least somewhat familiar. Where, oh where did those go? I'm out of ideas of where that went. Okay. So, there's this vertical line that the graph is getting close to but never actually hitting, and then there's this horizontal line that the graph is getting close to but never actually hitting. Do you remember what a line that the graph is getting close to but never actually touches is called? Starts with an A. Asymptote. So, reciprocal functions have a lot of asymptotes to them. And when I say a lot, I mean, well, technically the reciprocals only have two. One vertical, one horizontal. Now, these asymptotes play a key role in these graphs. The vertical asymptote. Vertical lines, what do their equations look like? If I look at this vertical line, I want to write an equation for it, so I'm going to think about coordinate points it hits. It hits the point 0, 1, it hits the point 0, negative 1, it hits the point 0, negative 2, it hits the point 0, 0, it hits the point 0, 2. What do they all have in common? 0 for an x value. Would you agree with me that a vertical line has all the same x values? X equals 0 is this particular vertical line. Okay, horizontal lines. What do they all have in common? 0 in what part? The y values, which means this particular horizontal line is y is equal to 0. Now this is important because when it comes to these graphs, one of the things we talk about with graphs oftentimes is domain and range. Domain is input values or x values. If I look at my graph, x values go left and right. Does my graph go all the way to the left? Does it go all the way to the right? Does it hit everything in between? Yes, except for what? It never actually hits 0. It goes all the way over here, gets closer, 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 closer to 0, but then it jumps over it and starts up there, going all the way over. That means the domain of this particular reciprocal function is x is not allowed to be equal to 0. Technically, it's x is all real numbers except for x equals 0. We can shorten that down. That's 0 coming from the vertical asymptote. Range is the up and down of the graph. Does the graph go all the way up? Does it go all the way down? Does it hit everything in between? Everything except for 0. So the range, y is not allowed to be equal to 0. Again, all real numbers except y not equal to 0. This time, the 0 comes from the horizontal asymptote. So, today we are going to be graphing reciprocal functions. Now, reciprocal functions, just like any graph out there, if you really want to graph them by making a table, you can, but it gets more tedious. Reciprocal functions graph beautifully by transformations. The standard form of a reciprocal function, I'm writing this a couple lines down because I'm going to write some things above and below it, is f of x is equal to a over x minus h plus k. Don't mind me, just adjusting my camera to make it more easy to work with. Y'all seen equations with a, h, and k before? It's a rhetorical question, I know you have. Do we remember what a, h, and k can do to a graph? Start with h. Do you notice that h is right next to the x's? It adjusts your x values. When you talk about x values on a graph, think about which axis. Does the x-axis go left and right or up and down? Left and right, which means adjusting the x's adjusts the graph to the left and to the right. Now, because of the fact that the original function has a minus in it, it's trying to indicate that it does the opposite of what you would think it would do. Adding moves to the left. So if I add an h value, it ends up moving left. While if I subtract an h value, it ends up moving right. Okay. K gets added to an entire function. So it takes something and adds to it. The something, generally, if you have the entire thing, it's the output. And if you change a graph's output by a number, you're moving it either up or down. The plus in the equation says it's doing exactly what you think it should do. Adding will move up, subtracting will move down. A controls two separate things. A can control if there's a reflection and if there is a stretch or shrink. Now, stretches and shrinks on reciprocal functions are not really going to change the graph drastically. So, that's supposed to be a C, don't mind me. The stretches and shrink stuff, while it is true, it is not our focus in this class. We're going to focus on moving up, down, moving left, right, and doing reflections. Now the reflection, we didn't clarify what makes the reflection, kind of like we did the left and the right. What does a reflection do? Flips it. Now, specifically in this case, it's going to flip across the x-axis. If, do you remember what makes a graph flip? If it's negative. Now, note when it's a reflection. The typical graph, in other words, when A is positive, A is greater than 1, the typical graph will be in the top right and bottom left of where the asymptotes are. If it's been reflected, in other words, when A is negative, it will be in the top left and bottom right. Again, of where the asymptotes are. So our parent function shows our typical. When I mean top right and bottom left, I mean here's my crossing of my asymptotes, right, left, top, bottom. Reflection would be here and here. Okay. I'll put those rules back on because I know there's a couple people that are still writing there. today we're going to be doing some graphing. Sketch the graph, state the domain and range. Now, it says sketch for a reason. I'm not looking for graphs to be perfect. If I was looking for them to be perfect, we would be making a table. I am looking for them to have the general idea. Now, when it comes to having that general idea, the asymptotes need to be in the right place, and the curves need to be in the right quadrants. Now, I'm doing quadrants in quotation marks because quadrants are technically, in math, reference to the x and y axis. When I say quadrants here, I'm referencing compared to where the asymptotes are. Because as the asymptotes, or as the graph moves, the asymptotes will move with it. Now, as we do this, one of the things you're going to find that I do is I always state what transformations happened. So, I generally ask myself 3 things because there's 3 things we're focusing in on. I ask myself, did the graph move left or right? No. Now, you don't have to write it if it doesn't do it, but for the sake of our notes, I do recommend you write all of these down. Okay? Did my graph move up or down? See, shaking heads. Which one? Up or down, and how much? It moved up 5. Did it reflect? No. Number in front is positive, so no reflection, or no flip if you prefer. So these are the things that I either need to make my graph do or not do. So I'm going to make myself a little graph. Now I noticed it moved up 5 as its main movement, which means I probably need a little bit more room on the higher side of my graph. If it moved down, I would need more room downwards. If it moved left, I would need more room to the left. You do need to put markings on your axes. I will assume that if you number them, that you are counting by a scale other than 1, and if you don't number them, that you are counting by ones. The first thing I recommend you draw in are your asymptotes. The asymptotes were at 0 for the x's and 0 for the y's. Let's talk about that vertical asymptote that would typically be here. Now, the asymptotes undergo all of the different transformations as well, but you're not going to notice vertical lines doing a whole lot of things. Are you going to notice the vertical line moving to the left or to the right? Yes, but this one didn't. Are you going to notice the vertical line moving up or down? No, they go indefinitely. You're not going to notice. Are you going to notice the vertical line flipping over? No. So vertical lines, you only have to worry about the left and the right. Since there was no left and right, my vertical asymptote stayed right here, and do mark the equation on the asymptotes. In this case, it didn't move, so it's at 0, but what equals 0? X. Horizontal lines, similar in idea. But are you going to notice a horizontal line moving to the left or to the right? No. Are you going to notice it moving up or down? Are you going to notice it flipping over? No. So up and down is all I have to worry about. Up 5, typically it's at 0. 1, 2, 3, 4, 5. Y equals 5. To finish it off, I make the actual graph. The graphs are these arcs in opposite corners. Do I stick in these corners? Option 1. Or are they going to be in these corners? Option 2. There's no reflection, so it stays where it originally should. Now, your graph should get close to the asymptotes without touching them in both areas. Flatten out by the asymptotes. If you accidentally hit the asymptote, it's okay. It's not the end of the world. Just don't go like full on through it. Ta-da, I graphed. Domain is based on the vertical asymptote. It's, find your asymptotes, put a not equal to them. That's going to give you your domain and your range. Domain is x's. My x's are not allowed to be equal to 0, because that's my vertical asymptote. My range goes to y values. Y's are not allowed to be equal to 5. Y'all think you can graph some reciprocal functions? I think so too. One thing that I will note is if there is a reflection, it could show up in the actual top of the fraction, or it can end up in front of the fraction. For example, that negative is a reflection. Nope, that's not FST. Page 549, questions 7 through 21, just the odd problems.